Hi, David. Hi, Abu.
Hello. Hello,
How's
Professor.
Hello.
everybody?
Very
Hi,
good.
Karen.
So he named Ron's son. Guess he didn't want anybody to forget whose son I was.
Okay, we're recording and I'm going to pin this and you're going to tell me if the focus is good. How is it?
It's good.
How are you tonight?
Good.
All right. David, you were here first, so you get to ask the first question.
Look at this.
Well, uh I just had a question about so you listed like a couple of problems at the end of last class.
Yes.
Is that what's gonna be on the test?
Well, not exactly those problems, but
Yeah.
it's a pretty good representative list. It represents about 90% of the problems, I would say.
Okay.
I always have a couple of thinking problems where I ask you to write in your own words about something to see if you understand it. But the great majority of the test will be similar.
Okay.
It's a good question.
I'm basically here to just like date low key. I
Just
don't
soak
really
up. You're just here to soak it up.
yeah.
All right. I'm here to dish it out.
Yeah, if I have a question though, I'll definitely ask you.
Okay.
Yeah.
Abu, do you have a question, a particular question or a problem you want to look at?
Well, no. Oh, just like was doing a problem, and I just wanted uh
All right, hang on just a sec. My dog is barking. He wants to come in from the rain. Hang on, hold that thought. All right. Sorry about that. Okay. Is there a particular question or a general question or what you got for me?
yeah, it was a particular question. It was a device question. Guess it was if A divides B and A divides C.
All right, will you read it to me? What number was it?
It was from the notes that you had for device. I mean, I can go ahead. I can.
Was it from day 14 notes?
Pretty sure I have it all. It's coming.
Because I can bring those notes up and look at them,
I was
but I don't know which one you're talking about.
it's like it's okay. Oh yeah, it's actually the 11 and
Is it number 4?
for section 4.
Is it from day 14 notes or is it a different question?
The 11. Is it?
Number
No, the
11?
11. No, it's
There
actually
isn't a number
question
11. I'm
example
sorry,
B from the
Abu, I
11.
don't understand. From day 11. All right, let's take a look at day 11. Can you tell me which example it is?
Number 3.
Is it example 3?
Yes.
We have example 3, example 4. Oh yeah, I that's all there was to it. On example 4,
Is it 4 or 3?
I don't know.
3.
Example 3?
Yes.
All right, what about example 3 did you not understand? Let's look at it. It
I was
says
just writing the conclusion.
the conclusion.
Yeah. So it's just like a small part of it that I have a question about.
Okay, so it says for all A, B, and C in Z, if A divides B and A divides C, then A divides the sum, B plus
Mhm.
C, right?
Mhm.
It's a very basic question about divides. It's one of the first properties of divides. So we have a hypothesis, and you said you had a question about the conclusion.
Yeah, just the conclusion, that's all.
So can you be more specific? Did you not understand what the conclusion was saying?
No, just, so I had uh, I was able to, solve it, and it does divide it, right? So now I'm writing and I wrote it as like a and an integer, and now I'm just saying a divides b plus c by the definition of divides. Would that be enough, or do I have to say more than that?
No, you can just say A divides B plus C by the definition of divides. You don't have to say B plus C equals A times M, where M is an integer. So that last sentence, this means B plus C equals A times M, where M is in Z. That's optional because you've already proven that, up here. You can just say, so A divides B plus C by the definition of divides.
Okay, thank you very much. That's all I had for that.
All right, this is sufficient.
Yeah. Aside from that, it's just contradiction.
All right, you have some questions about contradiction proofs.
Yeah,
Okay.
you know,
Do you have a specific question about proof by contradiction?
well, it can just be the one you went over in class.
The square root of 2 is irrational, or one of the other ones that, like, if x is rational and 2x plus square root of 2 is, then 2x plus square root of 2 is irrational,
Yeah,
or
that,
or
that,
example, for example,
yeah,
I think I should have numbered it example 3. I think I accidentally renumbered it.
yeah, any one of those would do, aside from
Okay,
square root.
I'll just say example. All right, let's look at it. If x is not equal to 0 and x is rational and y is irrational, then xy is irrational. Is that one okay?
Yeah, sure.
All right, so we have a big hypothesis P and a conclusion Q. So this is if P, then Q, right? So for proof by contradiction, let's just review. We're going to assume the negation of the statement we wish to prove. Show this leads to a contradiction. So that's our wish. And that means the original statement must be true. Because when we assume the negation, it leads to something that's impossible. Okay, that's the logic behind proof by contradiction. Assume the negation of the statement we wish to establish. Show this leads to something that's impossible. And then that means the original statement is true because the negation leads to something that's a contradiction. So when we write the proof, we need to be sure that we can write the negation. So what is the negation of if P then Q?
P and not Q.
P and not Q. Right. So in our proof by contradiction, we assume P happened and Q did not follow. So assume X is not equal to 0 and X is rational and Y is irrational. And what else?
XY is rational.
XY is rational. Good. Now, this hypothesis gives us a lot to work with. All right, let's take a look at all that we have to work with. We know X is not equal to 0. We know X is rational. That's going to give us an equation. We know XY is rational. That's going to give us equation. And then Y is irrational. That doesn't give us an equation, but it is part of our hypothesis. And we're going to contradict this because it doesn't give us an equation. That's all we can do with it.
So, Professor, I can see the what you are writing, but it's just a little bit blurry.
It's a little blurry.
Yeah, just a little bit, but I can see it.
Is that better?
Kind of like the same.
Well, let me bring it closer then.
We can't see the whole picture.
I know it's a choice.
Okay. Yeah. Well. Yeah.
Is that in focus at least?
Yes. Yes, it is.
Thank you for saying so, because it looked in focus to me before and it wasn't. How's that?
That looks good.
Okay. So we're assuming X is not 0 and X is rational. That's going to give us information. We're assuming XY is rational. That's going to give us information. In fact, it leads to a nice equation for both X and for XY.
Okay.
Knowing Y is irrational gives us no equation to work with. The only way we can use this piece of information in our hypothesis is to say, okay, I'm going to contradict that.
Okay.
That's all we can do with it, is try to contradict it. And the way we contradict the assumption that Y is irrational is by proving that the other parts of the hypothesis will show us that Y is rational. And that's going to be our contradiction because Y cannot be both irrational and rational. Does that make sense? Do you want me to say it again?
No, not all the way yet, or just the reason why the why is irrational. I know because we cannot make an equation out of it.
That's right. So how do we get to use that? You see, one thing that we learn when we're writing proofs is we need to use the whole hypothesis generally, unless there's some kind of what's called a red herring that's been included, and I don't do that because it's quite confusing. So the only way that we can make any use out of this part of the hypothesis is to actually use it to get our contradiction. We know we're going to try to find a contradiction. So these problems that I'm giving you are actually easier than the first example of proof by contradiction, where we had no idea what our contradiction was going to be. Remember, we assumed square root of 2 equals A over B, and we assumed A over B was written in simplest form or lowest terms, where A and B had no common factors other than 1. Well, that is kind of something that you have to be fairly clever to understand that you need to do. The problems that I'm asking you to work are all going to be fairly straightforward in that you're going to know something is irrational in your hypothesis, And you won't be able to use that to give an equation to work with. The only way you'll be able to use that information is to contradict it. And that will give you a direct clue to what your contradiction should be. Does that help?
Okay, so, yeah, but, yeah, because I know you explained that we need to have the why as rational, because then we have a definition for it, and then we can make it into an equation. I guess, what I'm saying is, can we just say, if it's showing as irrational, can we just say, like, negate that? Is that allowed?
No.
Okay,
All we are allowed to do is negate the entire statement. We have to negate this entire statement and show that the negation of this entire statement leads to a contradiction. We can't assume that Y is rational. We have to actually now prove that Y will be rational with all of these other parts of the negation that we are assuming.
okay,
Does that make sense?
yes, yes.
And then the rest of the proof is given in class. The rest of the work is the work that we did to prove that this, and this all force Y to be rational. And then that was our contradiction because we showed that this, and this forced Y to be rational, which then contradicted our hypothesis, which says Y is irrational. That's why we solved for Y in our algebra work in the class notes on day 14.
Okay.
All right, Karen, do you have a question? Hi, Joshua. I'm glad to see you.
Hey, yes, I do. I want to go over problem 8 that you gave in day 14 for proof by contradiction. I would like you to like show me, refresh like how I can do that with odd and even for all mn is an integer. If 2m plus 3n is odd, then m is even or n is odd.
Okay, if 2m
Plus
plus
3n
3n
is odd,
is odd,
then m is even or n is odd.
okay, good. Let's work through this.
For contradiction.
Yep. So here, our hypothesis is that 2m plus 3n is odd. That's our P.
Mm-hmm.
And our Q is this compound statement that M is even or N is odd, right?
Mm-hmm.
So this is an if P, then Q. So in our proof by contradiction,
We negate it.
yeah, we're going to assume, you tell me,
Um, assume 2m plus 3n is even. We wish to show m is odd and n is even. I don't know.
no,
Um,
no, because what is the negation?
and
What is it? It's P and not Q.
p and not q.
So we have to keep P just the way it is.
Mm-hmm.
So we assume 2m plus 3n is odd and not Q. M is odd and N is even. Does that make sense?
Yes.
So that's our hypothesis. And it looks like we've got a lot of equations, and we do. We've got that 2m plus 3n has to be odd. We've got that m is odd, and we've got that n is even. We've got all that.
Oh, so do we wish to show, would it be we wish to show this leads to a contradiction?
Yes, that's always the wish. We wish to show this leads to a contradiction. And this is not the only way you can prove this. Another way to prove it would be proof by contrapositive. But let's just work through the proof by contradiction for right now, okay?
Okay.
All right. By the definitions of even and odd, all right, let's go through it. 2m plus 3n is equal to what? You tell me
2k
what you
plus
want.
1. 2k plus 1.
Sure. 2k plus 1, where k is an integer. Now we know that m is odd, so let's write an equation for m.
Oh, wait, for 2m?
No, just m.
M is odd.
Yeah, 2m won't be odd. That's kind of part of the point.
Oh, so it's gonna be m equals to j plus 1,
Okay, good.
where j is an integer,
Yep.
and n would be n equals 2l plus 1, where l is an integer. No, 2l, yeah.
Yeah, I'm using a curly L because if I use an L that looks like a 1, it's going to be hard.
Okay.
Now, if you don't like my curly L, then we
Oh,
can
it's
use
cool. It's cool. It's good. It's good.
we can use like, X or something.
Mm.
Now we're wanting a contradiction. So let's just take a look at what we have to work with. We know what 2m plus 3n should look like. It should look like an odd number. It is constructed from m and n with these coefficients 2 and 3. So let's take a look at what this m and this n tell us about 2m plus 3n, okay?
Are we gonna put it in there?
Yep.
Oh,
So what does 2m plus 3n look like if we insert our equations for m and n?
2k plus 1, 12.
Good. But notice what happens.
Oh,
This is 4k plus 2 plus 6l. Do you agree?
mm-hmm.
And now we can factor a 2 out of every term
Wait, why are we factoring?
because we're getting ready to show that these two bits of information force
Or at
2m.
odds?
I know, that's what we're going to contradict
Oh, okay, okay, okay,
because these two bits of information force 2m plus 3n to be even.
okay.
And that'll be our contradiction. So let's just say we know that this x, which is the 2k plus 1 plus 3l, is an integer, right?
Mm-hmm.
Because sums and products of
Of the
integers
integers.
are integers.
Ma'am, instead of writing where when doing a proof to be faster, can you just put a comma and put k belongs to integer?
Yeah, you don't need that.
Okay.
That's fine. Good question. So 2m plus 3n equals 2x, x is in z, which means 2m plus 3n is even. So these two equations force 2m plus 3n to be even. But this bit of the hypothesis says that is odd. And an integer can't be both. But 2m plus 3n cannot be both odd and even, which is a contradiction. And that's the contradiction.
All right, that works.
Yes, it does. Now, let's look at proof by contrapositive of this same problem. You might like it better.
Okay. Proof by-
Day 14. So let's write the contrapositive just to look at it.
It's gonna be
For all M and N and Z, going to be not Q implies not P.
if M is odd and N is even, then 2M plus 3N is even.
Mm-hmm. And that's actually a little easier because we don't have to bother about a contradiction. We just start with not Q, and then we wish to prove not P, which is what we get anyway.
Mm,
See what I mean? So
yeah.
in proof by contrapositive, assume M and N are in Z and M is odd and N is even. What do we wish to show?
We wish to show 2M plus 3N is even.
Yes. And now we know how to do that because we just did it,
Yeah, okay.
right? Observe by definition of odd and even. We still have to build the equations, M equals 2K plus 1, K is in Z, and N equals 2J, where J is in Z. So 2M plus 3N equals 2 times 2K plus 1 plus 3 times 2J, which is still 4K plus 2 plus 6J, which is still 2 times 2K plus 1 plus 3J. And now we call that our integer X, and we explain, notice X, which is still the same expression we got in proof by contradiction, but now it's a little bit easier, is an integer because sums and products of integers are integers. So 2M plus 3N equals 2X, X is in Z, which makes it even.
Okay.
So either proof method works. Which proof method do you like better?
I would say they're both the same. It's just the beginning that changes.
That's
Low
right.
key. Like it's not like both of them to me are the same, low key, but yeah.
It's a little less work. Like,
For contrapositive.
yeah, because
Mm,
look, the contrapositive doesn't have to have this equation, and you don't have to say that there's a contradiction. You just prove that this is even and you're done.
mm-hmm.
So
It should always start with
if you can
contrapositive.
if you can use proof by contrapositive, do it.
Okay.
It's always a little easier. But some things are hard to prove by contrapositive.
All right.
Like if you have one rational and one irrational, that can be hard.
Yes, this is what I'm actually scared about, but I was watching your video on YouTube about it a bit.
Special topics,
Yes, but
good. I'm glad you watched that one.
yes, but that was mainly it's just the confusion about that, but I want to go back in the book and like trying to understand there. But thank you so much for
You're
helping.
so welcome. That was a great question. Okay, Joshua, do you have a question?
I was more so just like going through it with you guys. So I would say, can we do another, I guess, proof by contradiction?
Okay, can you pick one from day 14?
Give me 1 second to pull it up.
Hi, Sean. I'm glad you're here with us. Is it still in decent focus here?
Yeah.
Great, thanks.
I'm still looking for one that
Well, let me take a peek
specifically.
too. How about I take a peek too
Yeah,
at day
that's probably
14?
that's
I don't mind looking at that list. Uh,
because I want to get a long one that's more so I can like cover all the bases of going through it.
Proof by contradiction, a long
Yeah.
one.
Yeah.
I'll just make one up for you then.
Uh,
So you've already seen one proof by contradiction tonight.
yeah, I think I saw the second half of it 'cause I think I came in and you guys were already working on
Okay, well, the first half was just a review. Let's just quickly review the logic behind proof by contradiction. This was one we did in the notes on day 14. You assume the negation of the statement we wish to prove. So we assume the negation is what's true. We show this leads to a contradiction, and that means the original statement is actually what's true because the negation leads to something that is impossible.
Yeah, so we basically want to prove that the negation works, meaning that the original statement can't work if the negation's working.
No, proof by contradiction shows the negation doesn't work out, so the original had to be true.
Oh, so yeah, okay. Okay.
Okay, so I'll give you a new example. I don't know, I'll call it 13. I don't know why. For all x and y in the reals, if x is rational and y is irrational, then 5x minus y is irrational. All right. Now, this is a universal statement, and the hypothesis we can call P. And the hypothesis is that x is rational and y is irrational. The conclusion Q is that 5x minus y is irrational. So this is an if P, then Q type statement. Do you agree?
Yeah.
So now we're going to assume the negation is true for a proof by contradiction. That's always the first step. We always assume the negation.
And then the negation would be if P, well, P and not Q, right?
That's right. And that for all
Yeah.
turns to there exists. So assume there exist x and y in the reals such that, and I probably wouldn't even dink you if you forgot to say that part. But the main thing is that P happens and Q doesn't. So we keep P exactly the way it is. X is rational and Y is irrational. And because the negation is an and statement, not Q. 5x minus y is rational. Does that make sense?
Yeah.
Because the negation of irrational, it is irrational, is it's not irrational. Well, that means it's rational because it's got to be one or the other. And the beauty of proof by contradiction here is that it gives us so much more to work with than we had a minute ago. Like, let's look at what we would have had if we tried to prove this statement directly. We would assume P, and our wish would be to show Q if we tried to prove this directly, right?
Yeah, and I think it's pretty hard to do that with just only that.
Yeah, all we have is one equation that X is rational. And then Y is irrational. That gives us nothing. And then we're trying to prove something is irrational. How do we even do that? We don't have some nice definition or equation that we can show works out to say, oh, that makes it irrational, because we don't have that kind of nice definition for irrational. But when we assume the negation, P and not Q, now look what we've got. We've got X is rational. That's going to give us an equation. We've got that 5x minus y is rational. We're going to get an equation from that. Now, this bit of the hypothesis that y is irrational, we don't get anything from that directly, but we know we have to use it somehow. The only way that we're going to be able to use this bit of the hypothesis is to contradict it.
By proving that Y is rational.
Yes, we will contradict this because that's all we can do with it. So we wish to show, my blue is running out. This leads to a contradiction, i.e., in particular, we wish to show this forces Y to be rational, and that will contradict our hypothesis that it is irrational, because that's the only way we can possibly use that part of the hypothesis. Does that make sense?
Yeah, I'm starting to get it a bit better now.
And if you go, I sent a really long email with practice problems
Yeah,
and all this
I
stuff.
looked over it a little bit. I haven't had a chance
Well,
to
on
sit
my
down.
YouTube channel, I have a video in a folder called Special Topics. It's actually a two-part video, and it's this idea. So check that video out in the Special Topics folder,
Okay.
okay?
All right, sounds good. I'll probably check it out after this.
Okay. Yeah, because it takes hours for these videos to process that we have now, because I'm doing them in Panopto because I need to generate the closed captions. Okay, here we go. We've got two rational quantities, and we will make equations using the definition of rational. By the definition of rational, you can help me. We know. All right, you help me. X is rational. So X is going to equal what?
X equals, isn't it like two? No, it'd be X over like A over B, right?
Yeah, X equals A over B, where A and B are integers and B is not equal to 0. Okay. I'm just putting commas here because I know you're going to be under time pressure for the test, and this is okay when you're giving the definition. But if you're writing a statement that needs
Uh-huh.
an and, you should write ands, okay?
Okay.
Now, 5x minus y is also rational. So 5x minus y equals, let's use C over D. Why not? Where C and D are in Z, and now D is not equal to 0. Are you with me?
Yeah, I'm with you.
And now all we got to do is solve for y and substitute A over B into X, and it'll make y look rational. I'll show you. 5x minus y is equal to C over D, right? That's just
Yeah,
this.
as I said, we established that earlier.
But now we can put in A over B for X. You agree?
Yeah, because we're just subbing it in for X, which, yeah.
And now we've got 5A over B. I'll bring the minus CD over, and I'll bring the minus Y over as a plus Y. You with me?
Yeah, I was just saying this up and coming part is where I start to get a little tripped out, just
All
setting
right.
fractions correct so the statement actually makes sense.
Oh my gosh, did you see me jump?
Yeah.
That was a big lightning bolt that just
I would
hit.
say it's pretty bad over here too. I think
Okay,
it's supposed
so,
to stop in like 20 though, or something like that.
all right. Huh. Okay, let me show you what's going on. Let me show you how I got 5a over b from 5 times a over b. 5 times a over b. Well, that's really 5 over 1 times a over b. Do you agree?
Yeah.
And we multiply fractions bikini style. Just multiply the tops together and multiply the bottoms together.
So
That's how
yeah,
I'm
you can
getting.
just basically move the five to the numerator for
Yeah,
no real issue. Okay.
yeah. Now, I want to solve for y, and this is a negative y, and I don't like a negative y, but I can add y to both sides, and that brings the y over to the right side as a positive y. Are you with me?
Yeah, and then you just proceed
So
from there.
subtract the c over d from the right side, from both sides, and it comes over to the left side as a minus c over d. That's all that happened in this step.
Okay.
Now we need to get y looking like something over something, not a difference of two quotients, but a single quotient. And that's when we get the common denominator, which is b times d. And then the 5a gets multiplied by the d, and the minus c gets multiplied by the b. You can put minus cb or you can put minus bc. It doesn't matter. But that is our y. And this is part one of the definition of rational. We've got y looking like something over something. Does that help?
Yeah, I was just saying. Then we proceed with the other steps since we have y equal to something.
Yeah, but now we've got to address the other two parts of the definition of rational because our goal is to show that this hypothesis that x was rational and 5x minus y was rational forces y to be rational, which will contradict our hypothesis that it is irrational. So we have to address all the parts of the definition of rational. There are three parts. Look, x was rational, so it looks like a over b. That's only part one. We have to know that the numerator and denominator are integers. That's part two. And we have to verify the denominator is not zero. Now we got that for free here and here because x and 5x minus y were known to be rational. We assumed that. Here we're trying to prove y is rational, so we have to show it satisfies all three parts of the definition of rational. We've only got part one so far. We've got y looks like something over something. Now we have to talk about that numerator and denominator and explain why these are integers. And the last part, part three, is to explain why BD is not zero. So let me remind you how that happens. To get that the numerator and denominator are integers, we look at how they're constructed. What mathematical operations are being used to build 5AD minus BC?
Subtraction and multiplication because
Exactly.
yeah.
And BD only uses multiplication. So we can kill both of these by mentioning subtraction and multiplication. Since A, and we have to mention A, B, C, and D are integers, and subtraction is called differences, and multiplication produces products. So, and differences and products of integers are integers. I'll just call the numerator x, which equals 5a minus bc is nz, and y, I'll just call the bottom. Ooh, I can't call them x and y, can I? Because we already used x and y. I'll call them m and n. M, which is 5a minus bc, that numerator is an integer, and I'll call the denominator n, which is equal to bd, is also an integer. We've got part two of the definition of rational done. We're trying to prove y is rational. We've got it looking like something over something, and we've just argued why that numerator and that denominator are definitely integers. You can write r is an integer, and you can write n equals BD is an integer if you're more comfortable writing the words than saying is an element of the set of integers. You can do it either way. This is just a little quicker. Finally, we have to address the third part of the definition of rational. That denominator cannot be zero. But we've got this because remember, B was not zero and D was not zero by part 3 of the definition of rational when we set this up. Do you see how we used the part 1 of the definition of rational, that x equals a over b and 5x minus y equals c over d, and algebra to get part 1 of the definition of rational done? See, we use the part 1s to get part 1. Then to get part 2, that this numerator and denominator were integers, we used the part 2, that this numerator and this denominator and this numerator and this denominator were integers. See, we used that here, plus closure properties of the integers. And now to get the denominator BD is not zero, we're going to use the fact that these denominators aren't zero. So it always works out that way, that you use part 1 to get part 1. You use part 2 to get part 2. And now we're going to use part 3 to get that BD is not zero, part 3. Since B is not equal to 0 and D is not equal to 0, we see BD is not equal to 0 by the zero product property. You can just call it the ZPP. So Y is rational because we got all 3 parts of the definition of rational done for Y.
And we have to write that conclusion at the bottom, right? Like that. So Y is
Oh yeah,
rational.
you have to
meaning
have the contradiction because if we don't write this, then we
that-
won't be
Mhm.
able to contradict our hypothesis that it was irrational.
Okay. I was just double
And
checking.
then we have to write the specific contradiction, which contradicts our hypothesis that Y is irrational. And if you look at the class notes from day 14, you will see that in the margins, I wrote be specific, about the contradiction. To get full credit, that is always expected. And you can stop there. If you want to give a conclusory sentence that says that means, for all A's, and so this is optional. So if X is rational and Y is irrational, and I know you'll be running out of time, so you may not want to write this, you've got to write the contradiction. But you could say then 5X minus Y is irrational. And that's just a restatement of the original statement, but that's optional. This is optional. Okay?
Yeah, sounds good. Thank you.
Yeah, and I'm going to say again, see the special topics playlist. In YouTube. And that's at Liz Good 2766. Because I've got a recording
I was
of,
just,
of a
I'll probably watch it after I get out of here. I'll probably listen to a few more. Actually, I don't know if you're doing it anymore because we're running a little bit. Are you you're only going till 8, right?
it is the night before a test. I try to be kind of nice. I try to, somebody's got to, and I haven't even gotten to Malayla yet, and she's come in the room, so I want to ask her if she has a specific question for sure.
Okay, because I was gonna say I'll probably just watch more. You answer more people's questions. Just
I'm so
go.
glad that you've come to office hours. I think office hours are very valuable. We've been doing them twice a week at least. Like some weeks we've done 3, even 4.
Mhm.
And it's just such a great time to come and ask questions that are important to you.
I was gonna say yeah, I try to catch as many as I can, but with work and stuff, it's a
Oh, I
little rough
know.
sometimes. But that's why I was a little bit late to this one. I was like, oh, let me hurry up,
Oh,
put my.
I'm so glad you came.
Hmm. So, yeah.
Malayla, I'm so glad you're here. Do you have a specific question?
Yes.
All
Um,
right.
I have a question about special homework 6.
Number 6. Okay.
No, special homework 6, question 4.
Okay. Let me grab that and take a look at it. Hang on. So glad you're asking. Special homework number 6, problem number 4. Let me take a peek. Oh, that's get the standard factored form of n equals 55440.
Mm-hmm.
Can you see this okay?
Yes.
All right. So I think you see when we write numbers that are more than 3 digits, like 1,000 or 1,000,000, we put commas every 3 digits from the right. So this is a single number. 55,440. This was not 2 numbers.
Mm-hmm.
So let's get a calculator. Bring your calculators tomorrow. All right, 55440. I'm going to try to divide it by 2 first. All right, so 55440 equals 2 times 27728. Now I'm going to keep dividing by 2 until I cannot divide by 2 anymore. No, that's 220, my bad. 2 times 27720, duh, because it's half of 40 is 20. Okay, now 27,720 is even, right? It's got a factor of 2 in it, so let's divide by 2 again. So now we've got 2 times 2 times 13,000, excuse me, 860. Well, 13,860 is an even number because it ends in 0, 2, 4, 6, or 8, so we will be able to factor 2 out of that. So let's divide that by 2 and see what's left. 6,930, 6,930. Well, that's still even, so we can pull out another 2. So 2 times 2 times 2 times 2, I'll divide it by 2 again, and we're finally getting a number that's not even. 3,465. Are you with me?
Yes.
Now, we're going to just work our way through the primes in order, because I don't want to miss any. So what's the next prime after 2?
Sorry?
What is the prime that's next in size after the prime 2? We're just factoring out prime factors.
3?
Yeah. And I have a trick for you for figuring out if a big number is divisible by 3. It's kind of nice. Take the digits of the big number. So here, 3 is a digit, 4 is a digit, 6 is a digit, and 5 is a digit, and add them up. So 3 plus 4 is 7, plus 6 is 13, plus 5 is 18. Is 18 divisible by 3?
Yes.
So that means 3,465 will have a factor of 3 in it. It works for 9 too. If it's divisible by 9, if the sum of the digits is divisible by 9, then so will the number be. So now we're going to divide this by 3 because we know 3 is a factor. 1155. All right, let's see if there's a 3 in that because we keep using 3 until we can't use 3 anymore. So 1 plus 1 is 2. 2 plus 5 is 7, plus 5 is 12. Is 12 divisible by 3?
Yes.
So 3 is going to be a factor of 1155. So this, we can write this 2 times 2 times 2 times 2 as 2 to the 4th. And now we have 3 times 3. And now we're going to divide 1155 by 3. And we get 380. 85. Let's check for another factor of 3. What is 3 plus 8 plus 5?
16.
Is 16 divisible by 3?
No.
That means 385 won't be either. So we're done with threes. So we can bring these two together as a 3 squared. What's the next prime after 3?
5.
Will 5 divide into 385?
Yes.
Uh-huh. So let's divide it by 5. And we get 77. So let's keep going with 5 until we can't factor out any more 5s. Is 77 divisible by 5?
No.
What's the next prime after 5?
7.
Is 77 divisible by 7?
Yes.
In fact, it's 7 times 11. And that's it, because 11 is prime. All these are the prime factors. So the number of prime factors, see, P1 is 2. P2, prime number 2, is 3. Prime number 3 is 5. Prime number 4 is 7. And prime number 5 is 11. So the number of prime factors, K, is, we have 5 of them. We have 5 different prime factors. And then the rest, I think you know how to do, right?
Yes.
Okay, good. Do you have other questions?
Could we do number 5 too, please?
Sure. All right, so we're going to consider this expression for an integer x. X is equal to, I gotta make this a little bit bigger. Two to the fifth times 3 times 5 to the 7th times 7 squared times 11 cubed times k. Find the smallest integer, k, that makes x a perfect square. Were you in class the day that we discussed this kind of problem?
I don't think so.
We proved something about perfect squares. Recall fact 1. And I can point you to the day of notes in a minute. If x is a perfect square, then, oh, and x is greater than or equal to 4, which is, don't worry about that so much. I'm not going to give you, I'm not going to, I'll give you that part. Then every exponent in the standard factored form of x will be divisible by 2. Okay, it's just a fact that every exponent in a perfect square is divisible by 2. Hang on, I'm looking for the class notes where we talked about that. think it's day 11. Yeah. Let me share my screen. On day 11, we talked about the standard factored form in general, where n is bigger than or equal to 2, and its standard factored form is prime 1 to exponent 1 times prime 2 to exponent 2, all the way to prime k raised to exponent k. And the p's are prime, and they're in ascending order by size. P sub I is less than P sub j. So like P sub 1 is less than P sub 2 because 1 is less than 2. So these indexing numbers give us the order in which the primes are listed, and each of these exponents is a positive integer. And so we practiced that. But then we looked about this fact 1. We proved it. So we said we assume x is a perfect square, so it looks like n squared. And since x was big enough, n is at least 2, and it has a standard factored form. So then we looked at x. Well, x is n squared. So we applied this exponent of 2 to n. And using laws of exponents, that 2 comes in and gets multiplied by each of these exponents. And this is the final standard factored form of x when x equals n squared. See how every exponent has a factor of 2 in it?
Mm-hmm.
And so that's a fact about perfect squares. Their standard factored form has exponents that are all divisible by 2. So that means our job is to look at these exponents. So the exponent on the 2 is a 5. The exponent on the 3 is a 1. The exponent on the 5 is a 7. The exponent on the 7 is a 2. And the exponent on the 11 is a 3. So the 5, the 1, the 7, and the 3 are not divisible by 2. The exponent on the 7 is 2, so it is already divisible by 2, so we're not going to have to do anything to correct that. But this integer k is an integer that we build to correct these exponents, the 5, the 1, the 7, and the 3, to bring them up to an even number. So when we use k, you see we've got 2 to the 5th. We need one more 2. So we need a 2 because then we'll have an extra 2 that will combine with this 2 to the 5th to give us 2 to the 6th. I'll show you in a minute. This 3 is being raised to the 1, but 1 is not even, it's odd. So we need a 3 to correct this 1 and make it into a 2. The 7 on the 5, this exponent 7 is not even, so we need another 5, and that'll give us 5 to the 8th. The 7 is fine because it's already being raised to an exponent that's even, but the 11 has an exponent that's odd. We want that exponent to be even so we can add a factor of 11. So if we use this for our k, it will correct all of these exponents. Let's just look. Now, x, which is 2 to the 5th, times 3 to the 1, times 5 to the 7th, times 7 squared, times 11 cubed, times k, becomes 2 to the 5th, times 3 to the 1, times 5 to the 7th, times 7 squared, times 11 cubed, times 2 times 3 times 5 times 1. And now this 2 can come over here with this 2. So we have 2 to the 5th times 2. And we have a 3 to the 1 times that 3, which, these are to the 1, of course. And then this 5 to the 7th can combine with times that 5 to the 1. The 7 squared just stays the way it is because it's good already, because 2 is even. And 11 cubed, and this is 11 to the 1. And now when we gather these up and use laws of exponents, when we're multiplying like terms, we add the exponents. So this is now 2 to the 6 times 3 to the 1 plus 1, which is 3 squared, times 5 to the 7 plus 1, that's 5 to the 8, times 7 squared, times 11 to the what?
11 to the 4th.
Perfect. And notice all of these are now even.
Mhm.
And
So
that
that was
means,
the point, making it even.
yep. And now we can show this is a perfect square because it's this squared, and that's our n squared. Because it's only when all of these are even
Mhm.
that we can pull a factor of 2 out of each of these exponents and put it out here. And this is our n. This is, where our n is 2 cubed times 3 times 5 to the 4th times 7 times 11 squared. See? So do you want me to make you up one to do later, to work on?
Yes. Yes, please.
Find the smallest positive integer k that makes x a perfect square. X is equal to 2 to the 5th. Oh, let me change that. 2 cubed times 3 to the 4th times 5 times 7 to the 7 times 11 to the 9th times 13 to the 4th times k. I'll make that a 13 to the 6th, actually. Okay.
Okay. Thank you.
You're welcome. Okay, folks. I think we're going to call it a night.
Thank you.
You're welcome.
Thank you, Dr. Good.
You're welcome. I'll see you tomorrow.
I'll see you tomorrow.